Hi. Hello. Oh dear, the echo. It is. She's real. So hi, you may or may not have noticed I am not here today. I do have some doctor's appointments today. And so to make it kind of all fair to y'all, I did get to do a lecture with Block 5. And so I wanted to be able to take this opportunity to give you a lecture as well. I'm sorry, I am very sweaty. I've been chasing around my dog who has been eating plastic plant leaves and then hiding with them. And so I've been trying to get them away from her. And then also, sorry for this weird camera angle. Mainly just because all of our worldly belongings are right behind me here and here. And y'all don't need to see that. So you get to see Miss Green's like weird disembodied head. I kind of look like an egg. So hi. So I hope you're having a good day so far. Our attendance question for today is going to be, what are you saving money up for? What are you saving money up for? So I know a lot of you are at the age in which you are driving. And so you might be saving up for a car, for gas, because it's very expensive. Maybe for a trip once Miss Rona has made her exit. Maybe some clothes, maybe something fun to do this summer. And so we'll have a assignment in Google Classroom for you to submit your attendance question. I can't wait to see what y'all have. And so Miss Green is saving up for a house, as y'all know. It's still not built. And so hence why we have our stuff everywhere at my in-laws' place. But, you know, it could be worse. It could be worse, you know, like I guess the most stressful thing with the house thing is just Winnie finding every little nook and cranny to hide in because we have so much stuff. And so that's been the biggest challenge with this. We're lucky to have a house, so I'm not complaining. So I'm excited to see what y'all are saving up for within a society that's very consumeristic, very capitalistic, right? Money equals independence and the ability to express yourself and to hopefully do things that are fulfilling for you. So I'm really excited to read. All right, so we are going to continue today talking about atmosphere stuff. Sorry, there's a bug. And so without further ado, let me take us to our PowerPoint. So this is the same PowerPoint that was posted on our stream, on our Google Classroom. Oh, that's bright. And so on the third slide is going to be the holy guided notes, Batman. And so that is going to take you to this packet labeled atmosphere stuff. And that is where we are going to begin today. All right, so last time on AP, Environmental Science, we talked about unequal heating of Earth and how that creates sort of this three-factor, three-pronged situation. And so factor one is the variation in the sun's angle, right? And so we see, of course, at the equator, we have direct sunlight that covers a very small area because it is direct and concentrated. And as we move up in latitude, right, in either direction from the equator, we start to have this oblique angle. So it's much more spread out, so that direct ray is now kind of scattered or diluted, however you want to look at it. And so though it does cover a lot of area, it's not as strong. Okay. And so the factor two is the angle of incidence. Okay. And so this, again, is kind of explaining how these differing angles explain how the hottest part of the Earth is going to be the equator, and we get cooler and cooler as we move towards the poles. And so our factor three is albedo. And so this, as we will discuss later, guess what? Now is later. So if you head back to our PowerPoint, I have added some slides here, one of which is called atmosphere stuff, albedo, surprise. So let's take a look. So I am not going to do my Miss Green ASMR. I don't have anything to crunch, maybe like some papers. All right, so let's talk about factor 3, albedo. And so I'll read this little segment for you. You can include this in the packet where we've been taking notes and include that after that factor 1 and factor 2. Or you can put it into your digital notebook if that's what you've been doing, into your actual handwritten notes in your notebook as well. It's just kind of up to you. All right. So of the solar energy that reaches the atmosphere, about 1/4 is reflected by clouds and atmospheric gases. And another 1/4 is absorbed by carbon dioxide, water vapor, ozone, methane, and a few other gases. We also know those to be greenhouse gases, at least some of them. So the other half of the sun's rays / radiation reaches the Earth's surface, okay? So when this happens, some of that radiation is going to be reflected by bright surfaces like snow, ice, and sand. So that goes back to our analogy we we're talking about when you go to the beach, you have your toesies in the sand, and it's most of the time like a nice sensation, a little warm, you know. But if you end up walking towards the parking lot, which oftentimes is made of asphalt, it feels like your soul has left your body, along with multiple layers of skin off your feet, because it's much, much hotter. And that's going to have to do with this concept of albedo. Okay? So surfaces that reflect energy have a high albedo, so reflectivity. Most of these appear bright to us because they reflect light as well as other forms of radiative energy. I don't like that word, radiative. And so surfaces that absorb energy have a low albedo, surprise, and appear dark. So some examples of this would be black soil, pavement, dark green vegetation, and open water have low albedos. Okay. And so maybe you've had experience if you've ever gone skiing or snowboarding or have seen other people do so, that they usually have like mirrored glasses or goggles of some sort because of this phenomenon, right? Is snow and ice is white, and so it has a high albedo, meaning it's able to reflect very well. And so when that sun's radiation is reflected back out into space, that actually creates a very strong visual sort of aberration that is just hecka bright for humans. And so we have to have some sort of retinal, protection there. And so we'll talk more about how this albedo is going to be quantified. And so I have joined the Zoom as imposter Miss Green. And so that's why you hear this weird echo, and I apologize. I have tried to like turn down the volume on my iPad as much as possible, but she is like, no, we have to make this video as janky as possible. So bear with me, but I'm gonna go ahead and switch screens here. And so we are gonna talk about how we quantify albedo. Okay. Cool. All right. Boop. So albedo, once again, this is going to be the, it's mainly referring to like celestial objects, so rocks in space, which is Earth, and its ability to reflect. So Earth overall is not very good at reflecting because the majority of Earth is composed of water and land masses that have a lot of vegetation. And so those are relatively dark surfaces. And so they're not very good at reflecting. But we do have different parts of the Earth, specifically different biomes, which I'll define that for you in just a moment, that have differing abilities to be able to reflect this radiation back into space. And so albedo is going to refer to reflectivity. And apparently, if you play Genshin Impact, the game, there's a character named Albedo, but it's spelled like albedo. And so albedo equals reflectivity, and apparently a anime character in a game. You're welcome. Okay. And so when we are looking at ice/snow, okay, this is generally going to have a very light coloration to it. And so we'll say white slash bluish, and it's kind of more of a light bluish. And this is going to be within a biome of Arctic. It's an Arctic biome. And so to define biome, we're definitely going into more details about biomes after we get through sort of our seasonal patterns of wind and water currents and all that good stuff. We'll talk more in depth about biomes, but to kind of give you a rough definition of what a biome is this is going to be a region of distinct, let's say animals. Let's not be fancy and be like fauna and flora. We'll say animals and plants. In plants that is characterized by that region's climate. Okay. And so we talked at the beginning of this atmosphere stuff packet, the difference between weather and climate. And so to kind of give you a quick refresher, weather is going to be sort of that short-term experience that we have with what's happening within our atmosphere. And so it could be sunny outside, could be raining, who knows, because it is Florida. And so it could change in a matter of seconds or minutes. And so that short-term sort of status of the atmosphere is going to be considered weather. Climate is going to be long-term and not just like a couple of years of a pattern, but specifically decades. Okay, over decades, it could be several decades of a particular region's sort of precipitation and temperature that is going to determine its climate. So if we were to describe Florida's climate, right, it's a wetlands climate. So it's a wetlands biome. And so that's going to be characterized by a lot of humidity, a lot of standing water, and water being present all year round, right? And so we also have desert biomes, temperate forest biomes, we have our Arctic biome, we have, oh my God, my brain just blanked, tropical forest biome, we have our tundra biome, we have boreal forests. And so we have these kind of ways of being able to characterize a region based on this climate. And that is the main driver of what can exist there, right? And so for our Arctic biome, it's one of the very few places, one of the very few biomes that is good at reflecting sun and radiation back into space, but specifically it's the best biome for doing so because it's the lightest in coloration of all the biomes, okay? And so how we quantify albedo is going to be by albedo factors. And so how these work is, if you recall from our definition of albedo, it discusses how a quarter of the radiation from the sun is stopped by various processes, another quarter is stopped, but then half of the radiation continues onto the Earth's surface. So if we continue to think of that half reaching the Earth's surface, let's say there's 100% of that half that's happening. So we go boom. Okay, this is 100% of that sort of amount of radiation going towards the Earth's surface. Okay. And so depending on what biome it hits, right, we're going to have varying degrees of reflection. And so specifically for an Arctic biome, we are going to have an albedo factor. If I remember correctly, I think this albedo factor is 0.8. Okay. And so what that means is that 80% of incoming light and therefore radiation is being reflected back into space. Okay. And so this concept is really important because if you think back to when we first started talking about the greenhouse effect and greenhouse gases, the greenhouse effect is the whole reason why we're here, right? Without the greenhouse effect, i.e. having greenhouse gases to trap some of the sun's radiation near our surface, this rock we call home would be way too cold for us to even exist, right? So we rely on that retaining of heat to make it a habitable space, right, for all organisms. And so it's really important to note that this is a good thing, that we do retain some of that heat coming in from the sun, okay? And so like anything in life, like Cheetos, hot Cheetos, snacks in general, things are good in moderation. And so this heating is good in moderation to keep us kind of in the sweet spot of existence, okay? And so you might be thinking, all right, if we have 80% of that radiation, that's a perfect arrow. You can't tell me differently. If you have 80% going out, what's happening to that other 20%, right? So we have 100% going in, 80% going out. The heck is with the 20%, okay? And so that 20%, as you might have guessed, is actually being absorbed. And so this is going to be heat that is retained at the Earth's surface, right? And again, to some degree, this is good, right? We need this. And so let's think about what happens when we melt ice and snow, okay? It becomes water, okay? So water. So when we were talking about water in large quantities, so if you've ever been on a cruise or like deep sea fishing, you might have noticed that the water is actually really, really dark, right? And so it's going to be a sort of like dark greenish blue, almost black color, especially if you've like gone into Google Earth and like played around. You can notice that a lot of these satellite images, right, actually kind of capture that darkness of the ocean. The ocean, a mysterious and terrifying place. So our coloring is going to be dark blue, green, almost blackish, okay, which is really, really dark. So again, once we're thinking about sort of how we compare walking on white sand versus walking on black asphalt, right? We know that this darkness, right, is going to be retaining a lot of heat. So it's most certainly going to have a different albedo factor for a high heat fact, okay? And so we would say these guys over here have a high albedo, right? Meaning I have high reflectivity. And then we would say water is going to have a low albedo as a result. Okay. And so when we are thinking about the sun's radiation that is able to reach the Earth's surface at 100%, at 100, as the kids would say, this guy actually has an albedo factor of 0.10. Okay, so what that means is 10% of our incoming radiation, okay, so it is basically what over here says, is being reflected back into space. So that's really not good, right? So if we only have, let's make this a skinty legend. If we only have 10% being reflected, you guessed it, that remaining 90% is being absorbed by the Earth's surface, right? And so when we think about climate change, one of those main talking points is talking about how our poles are shrinking, right? When we go to melt ice and snow because of increased emissions of greenhouse gases, that creates sort of that layer of gas molecules that traps that heat in excess, right? Way more than we need for survival. it causes these icy cold places to warm up. Sorry for that weird echo. And therefore start to melt, right? And so we experience this transformation from our Arctic biome transformation into our ocean biome. Okay. And so this transformation is very dramatic. It's devastating, right? We go from being able to reflect 80% of incoming radiation to only being able to reflect 10%. So that's a very stark difference, okay? And so once this kind of process is set in motion, it's very difficult to stop, okay? So no pun intended if you imagine a snowball that's traveling, down a hill or a mountain, and it's gaining speed, and therefore it's collecting more and more snow as it continues to travel. It's getting bigger and bigger, right? And so that's what's kind of explaining this concept. And so in environmental science, we call that positive feedback loop. Positive feedback loop. Okay. And so what this means is as we increase one variable, another variable is going to be increased. And as a result of that other variable being increased, the original variable is going to be increased, and so on. It's this vicious cycle that is very difficult to stop once it's in motion. And so to kind of give you a little bit more of a detailed idea. So we have our excess emissions of greenhouse gases, specifically carbon dioxide, which is really good at trapping in heat, which is good for us because, again, it keeps it roasty toasty here on planet Earth, but not so great when we have that excess, right? So it's trapping way more heat than is necessary for life to exist, and it's basically roasting us, and not in a fun way, okay? So we have an increase of heat because of this, right? And because of that increase of heat, we're gonna have an increase of melting of our caps, right? And so because of that increase of melting, we're gonna have an increase of absorption of heat, right? Because we are now talking about transforming ice into ocean, right? And once we do that, right, we're absorbing more heat, making it hotter, increasing the heat, our original variable, right, which then increases the melting even further, which then increases our absorption, right? And so you can see how this is just going to be a continuous cycle, okay? And so we have a lot of these types of feedback loops within environmental science, but climate change, AKA global warming, is a big, huge example of this in action. And so you may be asking, okay, well, why is it that when we have global warming, right, we have politicians going into meetings about environmental legislation, about climate change, throwing a snowball and saying, there, you're global warming, right? When clearly, that's not what it means. And so when we refer to global warming, we're referring to this positive feedback loop, right? Where we're increasing the heat, we're melting our ice caps, and therefore increasing the absorption of radiation onto Earth's surface, and so on. And so when we do that, yeah, the catalyst, or the thing that's kind of the first domino in a chain of dominoes being knocked over, is going to be warming, right? And so it's that warming that is going to kind of set things in motion and kind of fulfill the prophecy of human downfall. And so because we are heating up specifically water, right? Think back to your infographics that y'all did on the different cycles, right? Our sulfur cycle, phosphorus cycle, nitrogen cycle, carbon cycle, very important. And then lastly, our water cycle. Water cycle happens because of the sun. Without the sun, we wouldn't have a water cycle, right? The sun is going to be the main engine, the main driver for that hydrologic cycle to take place. And so sun's heat comes down, heats up water, i.e. ocean, because that's going to be our biggest source of water here on Earth. And that is going to cause evaporation, evapotranspiration with plants. And so our water is up in our atmosphere, it condenses, it cools, and comes back down as precipitation, right? And so, yeah, we'll have increased rain, but keep in mind, precipitation can also be snow and sleet and hail. And so places where there's usually rain, there's going to be more rain. Places where there's going to be snow, there's going to be more snow, right? And so that's where that misconception about global warming isn't real, is because we have these sort of all out, dragged out, crazy cold fronts that are happening in places. But it's because of that sort of like a water cycle on a on a day with three monsters. I know a lot of you can relate to that. And it's just kind of like kicked into overdrive, right? And so that's going to speed up these natural processes, in which are normally kind of tempered and allowing for this, movement of macronutrients and micronutrients throughout our system, and kind of keeping everything nice and stabilized and at equilibrium. But as soon as we throw that wrench in, right, our greenhouse gases to trap the heat, we are effectively changing the course of so many different cycles. But when it comes to climate change, that biggest one is going to be our water cycle, right? And so we're going to have increased precipitation. Being in Florida, right, we're going to have an increased we're going to have frequent hurricanes. And those hurricanes that are happening, they're going to be severe, right? They're going to be kind of increasing in the damage that they do, right? Because if you think about hurricanes, their whole reason of being is warm water, right? And so that's why hurricanes slow down once they, make landfall, is because, they do hit obstacles like buildings and houses and cows and all that good stuff. And so, of course, that's going to cause a physical barrier to slow it down. Same thing with coral reefs. When we talk about our mangroves, those sort of means of phytostabilization, so stabilization of the earth using plants, right? That's going to slow down a hurricane. But further, the lack of water, but specifically warm water, causes that hurricane to drastically lose its power, right? And so if you think about how we're increasing the instances of hurricanes due to heat, sort of being pumped onto our Earth's surface, and water being really good at holding in heat, it has a good heat capacity, that is going to basically be like kind of souping up, giving a hurricane like a V8 engine and just saying, have fun, don't crash the car, right? And so that explains why it's called global warming, but more specifically, it's changing the climate. The warming is what's kind of creating that change, right? So hopefully that makes sense. Cool. So let's go ahead and let's go back to our PowerPoint. So we do have some practice questions on here involving albedo. And so the first question is asking, which of the following is the best description of albedo? Okay. Again, on the AP, we want to look at this word that is best. Okay, because there might be some of these answer items that might, apply, right? Like multiple of these items that apply, but we want the best description. And so right off the bat, I can tell you A is correct. Okay, so the ability of an object to reflect light. Okay, and so, yeah, I guess the ability of an object to absorb light, kind of, right? Because if it has a low albedo, that means it has an ability to really absorb light, but it's not going to be the definition of albedo. And then further, I would say E, technically, I guess you could say, it helps describe albedo because it's based on the coloration. But why does the color matter, right? And the color matters because of its reflectivity. And so that leaves us with A being the best description of this concept. For number 2, which of the following has the highest albedo? I've kind of already given you that answer. It's going to be B, fresh snow, okay, because it's going to be white, meaning it's going to be very high in its reflectivity. If I were to go through and rate this, I would say number 2 would be croplands. Oh my gosh, y'all are gonna judge me. Because I'm 12 years old, I was thinking for number 2, number 2, instead of croplands, I would say craplands. So number 2 is craplands. I know y'all don't miss me. I know you're happy I am not there. Generally, because croplands are going to be lighter in color, especially once fields are left to fallow and kind of, I guess, recuperate before the next growing season, it's going to be very light in coloration. Next up is going to be forest. Obviously, we have different types of forest, but just forest in general. From space, when we are taking satellite images, forest is generally a very dark green, right? So it's dark, but it's not too dark. Next up, I would say water, right? Because water is even more of that kind of deep, dark green / blue. And then last, but definitely not least, especially if you've had your footsies assaulted on asphalt, that's going to be last, because it's going to be the darkest out of this sort of set of answers. And therefore, it's going to have the lowest albedo, and therefore absorb the most light, and therefore be the most soul crushing when you step on that barefoot. Okay. And so hopefully this is kind of straightforward for you. I'm not sure if the AP is going to test you necessarily on albedo factors, but what's going to be really important, of course, is understanding that the factor itself is describing what percentage is being reflected. And so if it's asking, if something has an albedo factor of 0.3, how much of that solar radiation is being absorbed, you got to think, all right, so the albedo factor is talking about reflectivity. So therefore, to find out how much is being absorbed, I need to figure out the other part of that 100% of radiation hitting the Earth's surface. So if it's a factor of 0.3, that means 30% of that radiation is being reflected back out into space, leaving 70%, because most of the time percentages add up to 100%. And by most of the time, I mean all the time. That's why it's percent, right? So per 100. And so that means 70% is being absorbed. If it has a factor of 0.3, 30% is being reflected, 70% is being absorbed. And so I think 0.3, that's usually like a desert biome, because generally that's where you have like a lot of beiges, taupes, tans, light browns. I would know because I'm from Arizona, in case y'all didn't know. And so that is going to be, pretty good at reflecting, but of course it's not going to be as effective as a completely white surface like ice or snow. Or my smile. I'm kidding. All right, so go ahead and take this moment to take a break. And so take 3 to 5 minutes, get up, stretch, walk around, do some jumping jacks, go to the bathroom. If you're in person, please ask first to go, just don't get up and leave. If you're at home, grab a snack, do a drive-by pet of your pets, all that good stuff. And I'll meet you back here to talk about weather and storms and the Coriolis effect, which sounds weird and like from a sci-fi movie, but I promise it's real. All right, so I'll see y'all in just a second. Bye. Oh.